Hello and welcome to this A-Level Chemistry explanation video about acids and bases. In this video, we'll start by exploring pH curves, what they can look like and how we generate them. From there, we'll move into looking at indicators and how we select an appropriate indicator for a titration. And we'll finish by exploring how we calculate the pH of mixtures. pH curves show how pH changes during the reaction of an acid and a base. In this reaction, one chemical is added to another in a titration style experiment. And so you would have one chemical in the conical flask, I'm showing it as a weak acid here, and the other chemical would be in a burette. And for me, I've got a strong base in my burette. And to generate a pH curve, you would measure the starting pH with a pH meter, or you might call it a pH probe, and then you would gradually add more and more solution from the burette, swirling every time you add some solution and measuring the pH every time you add more of your solution from the burette. And you would add the solution in smaller amounts the closer you get to the equivalence point for this titration. And this will give you a picture of how the pH changes as you add more and more chemical from the burette. In an acid-base titration, the equivalence point is the point in the titration where the moles of H+ ions is equivalent to the moles of hydroxide ions. And so the base would have neutralized the acid in my titration example that I'm showing here. The end point for a titration is the point in the titration where the indicator changes colour. And so this is an experimental observation. This topic is really important because it has links to two required practicals, or the practical assessed groups, depending on which course you are following. Firstly, in the titrations required practical, you need to be able to perform titration calculations and describe how to do a titration in the way that you learnt in the amount of substance topic. And in the pH curves required practical, you need to explain in great depth how you generate the pH curve itself. I go into greater depth about both of these in separate videos. You need to be able to sketch and explain the shapes of typical pH curves for all combinations of weak and strong monoprotic acids and bases. There are 4 that you need to know, and their precise shape depends on whether you are adding the acid to the base or the other way around. I'm going to start by showing you the curves where a base is being added to an acid. First of all, if we start with a strong acid in the conical flask, the pH will of course begin at a very low level because strong acids have got a low pH. If we add a strong base to this acid, the pH will of course increase. Once we reach the equivalence point, the pH increases sharply and very quickly. And then when we are finishing our titration, the pH is very high because we're adding a strong base, and strong bases have a high pH. The equivalence point then is this point here where we've got this vertical region of our pH change, and the pH at the equivalence point for a strong acid, strong base is 7. For a strong acid weak base titration, again the pH starts low and it increases gradually until we reach the equivalence point. Again, I'm showing the equivalence point here, and then the pH changes rapidly and we finish with a pH that is not so high as before because we were adding a weak base to our strong acid, so we finish with the pH of a weak base. Do notice that the pH at the equivalence point, which is halfway up the vertical region at the equivalence point, and this will be less than 7, since the salt of the weak base is going to be a proton donor. And so that means that even though we have neutralized our strong acid, the salt that is produced is not actually precisely pH 7. This time, if we start with a weak acid and add a strong base to it, the pH will start low, but not as low as when we had a strong acid. And it will increase gradually until we reach the equivalence point. Then it will change quickly, it will increase rapidly, and it will level off at the pH of a strong base because the strong base has a high pH. Again, the equivalence point is where we see the rapid change in pH, and the pH at equivalence this time would be greater than 7, as the A- that is produced from the weak acid is actually a proton acceptor, and so this means at the equivalence point the pH will actually be greater than 7. And finally, if we take a weak acid and add a weak base to it, you can see that we start at the same pH as before, a below 7 pH, but not very, very low that you'd expect for a strong acid, and the pH increases gradually. We reach the equivalence point, and the pH changes from being an acidic point to a basic pH, so in other words, greater than 7, but there is no rapid change in pH at the equivalence point. But what we can say is that the pH at the equivalence point, you would expect it to be 7. When you add an acid to a base, you get 4 characteristic pH curves, and the shape of the pH curve for the particular titration depends on the relative strengths of the acid and the base. First of all, if you add a strong acid to a strong base, we obviously start with a high pH because of the strong base. Then when we reach the equivalence point, there is a rapid decrease in pH, and we finish with a very low pH because of the strong acid. The pH at the equivalence point is going to be 7 because we're using a strong acid and a strong base. When you add a strong acid to a weak base, the pH starts above 7, but not so high as the first example because we're only starting with a weak base. The pH decreases gradually, then we reach the equivalence point, and the pH decreases sharply to the pH of a strong acid. Notice at the equivalence point, the pH change is not quite so high as before because the pH wasn't as high as before already. And also note that the pH at the equivalence point is going to be less than 7 because the salt will actually be a proton donor. If we added a weak acid to a strong base, we again start with the high pH that decreases gradually. At the equivalence point, the pH change quickly decreases to the pH of the weak acid, and the pH at the equivalence point is going to be greater than 7 because the salt is going to be a proton acceptor. And finally, if we have a weak base and add a weak acid to it, the pH starts above 7, decreases gradually. At the equivalence point, there isn't really a sharp decrease in pH. There is just a point of inflection to the curve itself, and the pH at the equivalence point will be 7. Indicators are often weak acids that change colour based on the pH of a solution. This happens because they exist in equilibrium between two forms. First of all, we have the protonated form, which is typically shown as HIN, where H is the proton that the indicator could donate, and the IN is symbolising the rest of the indicator. And on the other side of the equilibrium, we have the proton that has been donated, and we have the IN-, which is representing the deprotonated form of the indicator. For something to be a suitable indicator, the protonated form and the deprotonated form of this indicator need to have different colours. At low pH, the solution has more hydrogen ions, and so the equilibrium will shift left and produce the protonated form of the indicator, and we will see that colour. As the pH increases, the hydrogen ion concentration will decrease, and so equilibrium will shift right and produce more of the deprotonated form, which has a different colour. Indicators change colour within a specific pH range based on their pKa. And the pKa for an indicator is the pH at which the concentration of the protonated form of the indicator and the deprotonated form of the indicator are equivalent. And typically, the pH range over which the indicator changes colour is its pKa plus or minus 1. In other words, it's approximately within 1 of their pKa. For example, phenolphthalein has a pKa of 9.4, and it changes colour between 8.3 and 10, so slightly less than 2 units wide. Similarly, methyl orange has a pKa of 3.7, and it changes colour over a narrower range, between around 3.1 and 4.4. While the exact range depends on the indicator, the plus or minus 1 rule is a helpful guide for understanding how indicators behave. When selecting an indicator for a titration, the best indicator to choose will be the one where the colour change, so that's the end point of the indicator, occurs during the rapid change in pH that occurs at the equivalence point. You need to be able to use pH curves to select an appropriate indicator. Now, importantly, the indicator that you choose needs to have a pH range that aligns with the rapid change in pH that occurs at the equivalence point. For instance, a strong acid, strong base titration has a very big change in pH at the equivalence point, between around 3 and 11. And so we need to choose an indicator that changes colour within this range. Two good examples that we could use are phenolphthalein and methyl orange. You can see that I'm representing the range over which these two indicators change colour, and both of these ranges align with the rapid change of pH that occurs at the equivalence point. For a strong acid weak base titration, you can see that the pH change is different. It is between 3 and 7. And so when we're choosing an indicator, the pH change of that indicator needs to fall entirely within that range. So of the two indicators that I've used previously, only methyl orange is appropriate because the pH range for phenolphthalein is too high. It's above that change in pH that occurs at the equivalence point. For a weak acid strong base titration, the pH change will be between 7 and 11 at the equivalence point. And so this time methyl orange would not be appropriate as its pH range at its endpoint falls outside the 7 to 11 range. Whereas phenolphtalene's endpoint coincides with this rapid change of pH at equivalence point, so it would be an appropriate indicator to use. For the pH curve for a weak acid, weak base, there isn't a rapid change in pH at the equivalence point, and therefore no indicator is suitable for this pH curve. You can see I'm showing phenolphthalein and methyl orange as definitely being inappropriate indicators, but even an indicator whose pKa was 7 would still not be appropriate because of that absence of a sharp, rapid change in pH at the equivalence point. The pH change would still begin before the equivalence point and finish after the equivalence point. And so the indicator would change colour over a range of different pH values and over a range of different volumes of base being added to the acid. In a titration, a base, for example sodium hydroxide, is added from a burette and reacts with a weak acid, HA, which is in a conical flask, and the acid is turned into the salt, A-, and water. Remember that the equivalence point in an acid-base titration is where the moles of hydrogen ions is equal to the moles of hydroxide ions. In other words, at this point, all of the acid has been neutralised and converted into A-. If 20 centimetres cubed of base is needed to react with all of the weak acid, it follows that 10 centimetres cubed of base would be needed to react with half of that weak acid. This is known as the half-equivalence point. And at this point in a titration, precisely half of the acid has been used up and converted into the salt, A-, and half of the acid is left unreacted in the conical flask. And this means that the concentration of unreacted acid, HA, is exactly equal to the concentration of the salt that has been produced, A-. The Ka expression for this weak acid will have Ka equals hydrogen ion concentration multiplied by salt concentration divided by unreacted acid concentration. And since the unreacted acid concentration is the same as the salt concentration, these terms will cancel out in the expression. And so it will simplify down to Ka is equal to the hydrogen ion concentration. And then if we take negative logs of both sides of this expression, the negative log of Ka is equal to pKa, and the negative log of the hydrogen ion concentration equals the pH. And so we can say that at the half equivalence point, Ka is equal to the hydrogen ion concentration, and pKa is equal to pH. You can carry out an acid-base titration in order to identify an acid using the half-equivalence point. You would do a titration once with an indicator and use the indicator's colour change to work out the volume of base added to fully neutralise the acid at the equivalence point. For instance, we might find 20 centimetres cubed of base was needed to neutralise the acid. And then you'd repeat the titration, only this time you'd add enough base to precisely half neutralise the acid. So for my example, this would be 10 centimetres cubed. And then at this point you would use a pH probe, or you might call it a pH meter, to measure the pH at the half equivalence point. And at this point, since the concentration of unreacted acid is precisely equal to the concentration of base that has been produced, Ka is equal to the hydrogen ion concentration. And so if we take negative logs of each of these terms, we get negative log of Ka equals negative log of the hydrogen ion concentration. And negative log of Ka is pKa, and negative log of hydrogen ion concentration is pH, and therefore pKa equals pH. And so we can say that the pH at the half equivalence point is equal to the pKa of the acid. And since acids have a specific pKa value, this value can be used to identify the acid. A common task in A-level chemistry is to be asked to calculate the pH of a mixture. For instance, in the situation that I'm showing at the bottom of the screen, where we're told that 20 cm cubed of strong acid, with a concentration of 0.1 moles per decimeter cubed, is added to 30 cm cubed of strong base, also with a concentration of 0.1 moles per decimeter cubed. And we're tasked with finding out the pH of the mixture. And of course, the pH of the mixture will be different to the pH of the separate solutions. And when these chemicals react together, one of them will get used up, that's the limiting reagent, and the other will be present in excess. And the method that you use to find the pH will vary depending on which of the two chemicals is in excess. Since we're being asked to find out the pH of this solution, the final step will always be the same, regardless of which chemical is in excess. We will need to do pH equals negative log of the hydrogen ion concentration. And so that means all of the previous steps will be working towards finding out what this hydrogen ion concentration is. The first few steps of this process are always the same, regardless of which chemical is in excess. Firstly, we need to calculate the moles of acid and the moles of base that we have at the start of this experiment. And this is most likely going to be done using the equation moles equals concentration multiplied by volume. And then it's worth looking at the formulae of the acid and base involved to see whether the acid is capable of donating more than one hydrogen ion, or the base is capable of donating more than one hydroxide ion. And if that is the case, we would need to scale that up by perhaps doubling the moles of acid to get the moles of H+, for instance. This step is not necessary for a weak acid, since weak acids only partially ionize. And then the next step is to compare the moles of hydrogen ions to the moles of hydroxide ions in order to determine which of the two is in excess, because this influences which of the pathways we then follow. The first of our three pathways is followed if we have a strong acid in excess. And this is the easiest pathway since strong acids fully ionize and we know the excess hydrogen ion moles. And so it's just that these moles are now spread out over a larger volume. And so step 4 on this pathway is to work out the new hydrogen ion concentration by taking the excess moles of hydrogen ions and dividing it by the new volume, which must be in decimeters cubed. And the new volume will just be the sum of the two individual volumes of the solutions that we reacted together. And then having got this hydrogen ion concentration, we would negative log that to find the pH. If we had a strong base that was in excess, step 4 here is also to find out the concentration of the excess ions. Of course, these are hydroxide ions, so we would take the excess moles of hydroxide ions, divide this by the new volume, again in decimeters cubed. And having got the hydroxide ion concentration, we then calculate the hydrogen ion concentration by rearranging the Kw expression. And so this gives us hydrogen ion concentration is equal to Kw divided by the hydroxide ion concentration. And then as a final step for this pathway, we would take the negative log of this hydrogen ion concentration that we've just found out. Perhaps the most difficult pathway is when we have a weak acid that is present in excess. Obviously, with it being a weak acid, we need to use the Ka expression to find the hydrogen ion concentration. And so the hydrogen ion concentration is equal to the Ka multiplied by the undissociated acid concentration divided by the conjugate base concentration. And in this case, the units are going to cancel out for this term on the right-hand side because we're taking one concentration and dividing it by another. And this means it's okay to use moles. So I've rewritten the expression with H plus concentration is equal to Ka multiplied by the excess HA moles and divided by the A minus moles. Now, the excess moles of acid, which we calculated at an earlier step, is easy to find. But the mistake that people often make is with the A minus moles. And the way that we find out the moles of A minus that have been produced is by looking at the moles of base that we used in the first place, or the moles of OH minus more precisely that we used in the first place, because the moles of conjugate base that we produce is going to be equal to the moles of hydroxide used. And so it's this term that we substitute in to our expression to find the hydrogen ion concentration. And you'd probably get a mark for this pathway for stating that the moles of A minus is equal to the moles of OH minus used. And then, having got this H plus concentration, our final step is to work out the pH by taking the negative log of this value. Calculate the pH of the solution formed when 50 centimeters cubed of 0.1 moles per decimeter cubed sulfuric acid is added to 30 centimeters cubed of 0.15 moles per decimeter cubed sodium hydroxide. The first step is to work out the moles of the acid and the base. Firstly, for the sodium hydroxide, moles equals concentration multiplied by volume. Concentration is 0.15 and the volume in dm cubed is 0.03. This gives us 0.0045 moles of sodium hydroxide. And since there is one hydroxide ion in each mole of sodium hydroxide, the moles of sodium hydroxide will be the same as the moles of the hydroxide ion. And then for the moles of sulfuric acid, moles again is equal to concentration times volume, so 0.1 times by 0.05 gives us 0.005 moles of sulfuric acid. Sulfuric acid is a diprotic acid. That means it has two replaceable hydrogens in its structure, so that means that the moles of the hydrogen ions will be double the moles of the acid. So we need to multiply that 0.005 by 2 and we get 0.01 moles of hydrogen ions. This then gives us an excess of hydrogen ions because 0.01 is greater than 0.0045. Quite how much is in excess we have to calculate. So the excess moles of hydrogen ions is the moles of hydrogen ions, 0.01, minus moles of hydroxide ions, 0.0045. This gives us 0.0055 moles of hydrogen ions. We need to then work out the new hydrogen ion concentration by dividing this excess moles by the new volume, which is 50 cm cubed plus 30 cm cubed, so 0.08 dm cubed. Once we've done that, we get a concentration of 0.06875. We then need to take the negative log of this answer to find the pH, and this gives us a pH of 1.16 to 2 decimal points. Calculate the pH of the solution formed when 25 centimeters cubed of 0.25 moles per decimeter cubed hydrochloric acid is added to 100 centimeters cubed of 0.2 moles per decimeter cubed sodium hydroxide. First of all, calculate the moles of sodium hydroxide by taking the concentration, 0.2, and multiplying it by the volume, 0.1. That gets us 0.02 moles of sodium hydroxide and the same moles of hydroxide ions. Moles of hydrochloric acid is its concentration, 0.25, multiplied by its volume, 0.025. That gets us 0.00625 moles of hydrochloric acid. This will be the same as the moles of hydrogen ions. Notice here we have no diprotic acid or no dibasic base, but it's always worth taking the time to check those formulae. So the moles of hydroxide is in excess because 0.02 is greater than 0.00625. Quite how much in excess? We have to subtract the 0.00625 away from 0.02, and that gets us 0.01375 moles of excess hydroxide ions. We then need to calculate the new hydroxide ion concentration by taking this excess moles value and dividing it by the new volume. So 100 cm cubed plus 25 cm cubed is 0.125 dm cubed. When we run this calculation, we get a hydroxide ion concentration of 0.11 moles per decimeter cubed. Since Kw is hydrogen ion concentration multiplied by hydroxide ion concentration, the hydrogen ion concentration is equal to Kw divided by the hydroxide ion concentration. And so we need to do 1 times 10 to the minus 14 divided by 0.11, which gets us 9.09 times 10 to the minus 14 moles per decimeter cubed. pH is negative log of this hydrogen ion concentration, and so that gives us a pH of 13.04 to 2 decimal points, proving that our strong base is present in excess. Calculate the pH of the solution formed when 30 centimeters cubed of 0.25 moles per decimeter cubed ethanoic acid is added to 20 centimeters cubed of 0.2 moles per decimeter cubed sodium hydroxide. Ka is 1.7 times 10 to the minus 5. This is a big clue that the weak acid is going to be found to be in excess, and so therefore we will need to use the Ka value. So the moles of sodium hydroxide is the concentration, 0.2, multiplied by the volume, 0.02. That gives us 0.004 moles of sodium hydroxide and 0.004 moles of hydroxide ions. The moles of ethanoic acid is the concentration, 0.25, multiplied by the volume, 0.03, which gets us 0.0075 moles of ethanoic acid. Now, since ethanoic acid and sodium hydroxide react in a 1-to-1 ratio, it's nice and straightforward to work out what the excess will be. 0.0075 is greater than 0.004. That means the weak acid is present in excess. So we take that moles of weak acid and subtract the moles of hydroxide ions away from it. So 0.0075 minus 0.004 gives us 0.0035 moles of weak acid, the ethanoic acid in this example. Then we need to recognise that the moles of A-, so that is the salt, that is produced will be equal to the moles of hydroxide ions that were used up in this reaction. And so that will be 0.004 moles of A- present in our product. Then we need to recognise that we have an excess moles of weak acid, so we need to use that Ka expression as we predicted. We need to find our hydrogen ion concentration. So we take our Ka value, 1.7 times 10 to the minus 5, we multiply it by our excess moles of HA, 0.0035, and divide it by our moles of A- that has been produced, 0.004. This gives us a hydrogen ion concentration of 1.4875 times 10 to the minus 5 moles per decimeter cubed. And then pH is the negative log of this hydrogen ion concentration that we've just calculated, and so the pH of this weak acid in excess reaction mixture is 4.83 to 2 decimal points.